This is a MacBook Air M3 logic board. Here's the Apple M3 chip, and directly next to it are two LPDDR5X DRAM modules. That's the shared memory. A bit further away, but still really close, are two NAND chips for the SSD. The other silver chip isn't NAND, that's for Wi-Fi and Bluetooth. A tightly integrated system and honestly amazing engineering from Apple. But it's nothing compared to an iPhone. This is what an iPhone logic board looks like. Suddenly, the MacBook Air board seems large and clunky. We can actually open up the iPhone logic board because it's a sandwich. The lower part is the RF or radio frequency board, and the upper part contains the SoC. In this case, it's an Apple A15 because this logic board was taken from an iPhone 14. If we turn it around, we can spot a single NAND chip. That's the iPhone storage. But wait, aren't we missing something? We got the A15 and the SSD, but where's the DRAM? Where is the shared memory? Every chip needs memory, but there are different ways to integrate DRAM into a system. The most common form are so-called dual inline memory modules, or DIMMs. Laptops usually use SO-DIMMs, which stands for small outline. They're literally just smaller. But we can go further. The next step is called on-package memory. That's what the M3 we just looked at is using, or Intel's Lunar Lake. Here the memory modules are placed directly next to the chip onto the same package. The obvious advantage is that you save a lot of space because you don't need memory slots and large memory modules. Plus, being so close to the chip has performance and efficiency benefits, but it also means you can't upgrade or replace your RAM if it fails. But there's one more step that's closer than on-package memory. It's so close, we can't even see the memory, or rather, we are being tricked because we can see the memory but not the SoC underneath it. Going all the way back to 2016 with the A10, Apple started using a very special packaging technology for the A series iPhone chips called InfoPop. It was developed by TSMC and is short for Integrated Fan-Out Package on Package. With InfoPop, the DRAM die is placed directly on top of the SoC die. It's a memory sandwich, package on package. That's why we can't see the DRAM on our iPhone logic board, because SoC and DRAM are a single closed package. InfoPop is used when space is the most limiting factor, like in a modern mobile phone. Stacking DRAM on top of the SoC means the logic board can be super compact, even if there are obvious downsides, like the thermal implications of practically placing a lid on the hottest part of your system. That's why the new MacBook Neo is so interesting. It doesn't use an M series chip like all previous Apple Silicon-based MacBooks. Instead, it's using the A18 Pro, the same SoC that powers the iPhone 16 Pro. Apple is using an iPhone chip in a MacBook. It almost feels a bit illegal. Can they do that, and how? The first question is, how much does the MacBook Neo actually share with the iPhone 16 Pro? Is Apple really using a tiny iPhone logic board inside a much larger MacBook? The simple answer is no. Every logic board is tailored to a specific product. It needs to connect and control dozens of different systems with the right control logic and connectors. The SoC, the A18 Pro, is just a part of that. Take the radio frequency board, for example. An iPhone is a mobile phone with a lot of connectivity aside from just Wi-Fi and Bluetooth, something the MacBook Neo doesn't offer. The iPhone logic board also needs to control a touchscreen and connect to multiple cameras, for example. The MacBook Neo is much simpler. One screen without touch functionality, a single 1080p webcam, keyboard plus trackpad, and speakers. That's basically it. That's all the logic board needs to handle. Oh, and the Touch ID sensor on the 512GB model. Thanks to teardowns like from iFixit, we can confirm this. The MacBook Neo doesn't use the same logic board as the iPhone 60 Pro. It's a new, larger design. Not as large as a M series logic board, but much larger than the logic boards in an iPhone. The only thing that the iPhone 16 Pro and the MacBook Neo actually share is the A18 SoC. You can see how tiny it looks on the larger Neo logic board. But isn't an iPhone chip too weak to power a MacBook and run macOS? Aside from the obvious fact that the MacBook Neo does so, let's take a look at what's inside the A18 Pro. Thanks to the guys from Chipwise, we actually have a great quality A18 Pro die shot. The chip contains about 20 billion transistors on a 109 square millimeter die and is produced in TSMC's N3E. It shares process node and most of its IP with the Apple M4 series. The best way to think of it is that the M4 and A18 Pro are the same chip generation, just built with different target devices in mind. Starting at the borders of the A18 Pro, we can spot 4 16-bit memory PHYs. They connect to the LPDDR5X memory chip that's later stacked on top of the A18 Pro using the InfoPop packaging we just talked about. And because 4 times 16 is 64, the A18 Pro has a 64-bit wide memory interface. According to Apple, the A18 Pro has a 6-core CPU with 2 performance and 4 efficiency cores. While the names are clear, performance core sounds fast and efficiency core sounds, well, efficient, it can be difficult to grasp the real difference. But looking at a die shot helps. The 2 performance cores are located in the upper left part of the chip. We can clearly see both cores in a mirrored layout side by side. Right below is the L2 cache with 2 8MB SRAM blocks for a total of 60 MB. This cache is shared between both performance cores. And below the cache, we can see a dedicated AMX unit, a special code processor that's optimized to run matrix operations, which are mostly used for machine learning. As you can see, the performance cores take up quite a bit of area on the A18 Pro, especially if you consider the large L2 cache and the attached AMX unit. In comparison, the efficiency cores are almost comically small. We can spot the entire cluster of 4 E-cores pretty much in the center of the chip. The E-cores share a 4 MB large L2 cache and also come with a dedicated AMX unit. As you can see, a single P-core is almost as large as all 4 E-cores combined. Make no mistake, both core types are great performing cores for their size. But looking at the silicon, you can see that there's a big size difference, which also translates into a big performance difference. E-cores are built to provide maximum single-thread performance and run at high clock speeds, a great combination for demanding applications. The E-cores, on the other hand, really focus on efficiency, but not just energy efficiency, also area efficiency. Next is the Apple Neural Processing Unit, or NPU. It does take up a large amount of area, similar to the entire E-core cluster. Apple calls it a 16-core NPU, but there are only 8 physical cores visible, which means they are most likely dual cores. Below the NPU and the E-cores, we can find the system-level cache. This is basically Apple's version of a chip-wide shared L3 cache. It can be used by almost all other system components. On the A18 Pro, the SLC offers 24 MB divided into 2 12 MB SRAM blocks. Last but certainly not least, we have the largest logic block of the entire chip. The 6-core GPU is located on the lower area of the die. Graphics are a very important part of SoC performance. Not just for gaming, but a modern GPU can accelerate many different tasks, for example rendering or even AI. If you think about it, there's a NPU, both P and E cores come with AMX units, and the GPU can also run AI. There's a lot of AI performance spread all over the A18 Pro. And with the A19 Pro and M5 series, Apple added so-called neural accelerators to the GPU. It seems like everything is converging towards AI acceleration. Now that we have labeled all major function blocks, you can see that there's still a lot of unmarked area left. There's some I/O on the upper shorelines of the chip, and I'm pretty sure that the top right part, next to the memory PHY, is the Apple Secure Enclave. The other areas are used for media and display engines, image and signal processing, and much more. But it's really hard to accurately labeling them without starting to guess. One more thing I want to mention is an interesting structure to the right of the P-cores. It's very clearly a dual core of some sorts. I call it low power E-cores. It most likely is a specialized embedded microcontroller, but it does look very similar to a tiny CPU. Now that we know what the A18 Pro actually looks like, let's compare it to the M4. Sadly, there isn't a similar high-res die shot available like the one from Chipwise, but we do have a low-res version from Tech Insights. Like we talked about before, the M4 uses the same IP and is built on the same N3E node as the A18 Pro. With 28 billion transistors, it has 40% more transistors, but at 165 square millimeters, it's about 50% larger in size. That's most likely because it contains more I/O and analog circuitry, something that usually has a lower transistor density. Looking at the die, we can see that the M4 has 8 memory PHYs instead of just 4 on the A18 Pro. Each one still offers a 16-bit wide connection for a total of 128-bit. The GPU is also much larger at up to 10 cores. Keep in mind that while the iPhone 16 Pro uses the full 6 GPU cores of the A18 Pro, the MacBook Neo comes in a binned version with only 5 cores active. A fully enabled M4 has double the GPU cores of the MacBook Neo, a pretty large difference. And that's why it needs double the memory interface, because memory bandwidth is most important for the GPU. Next, let's compare the CPU cores. The M4 has 4 P-cores, again double what the A18 Pro offers. But interestingly, both chips have the same amount of shared P-core L2 cache. It's 16 MB on the A18 Pro and the M4, and the same is true for the E-cores. While the M4 has 50% more cores, 6 instead of 4, the shared E-core L2 cache stays at 4 MB. The NPU is the same too with 8 dual cores, just like on the A18 Pro. But where it really gets interesting is the system level cache. The M4 only has 8 MB of SLC. That's a third of what the A18 Pro offers. A massive difference. But why? First, with a 128-bit interface, the M4 already offers a pretty decent memory bandwidth. There's less need for a large cache, which is mostly used to mask memory access times. And second, the A18 Pro has a much stronger focus on energy efficiency because it was designed as a mobile phone SoC. Every time the SoC has to access the DRAM, even if it's packaged right on top, it uses a lot of energy. Memory access is expensive. And with a large SLC, you are not only improving performance, but also power efficiency. That means if you would run an application that only uses 2 P-cores, but needs a lot of cache, the A18 Pro might actually be faster in certain tasks because it offers a combined 40 MB of shared P-core L2 cache and system level cache. Kind of cool if you think about it. But make no mistake, with double the P-cores running at higher clock speeds and 50% more E-cores, the M4 handily outperforms the A18 Pro in most scenarios. Just not in all of them. So what does all of that mean for the MacBook Neo? First, it shows that the A18 Pro is more than capable of powering a MacBook and running macOS. Yes, it's an iPhone chip, but in the end it's still Apple Silicon. It's basically a mini M4. And when it comes to on-die cache, the A18 Pro even has the advantage. Building an entry-level, low-cost MacBook isn't easy. Apple needs to cut costs without losing the essence of what a MacBook is supposed to be. And the A18 Pro is clearly part of that strategy. With a 50% larger die, a single M4 wafer produces only about 300 known good dies, while that same wafer could produce 500 A18 Pros. That's a big difference. Remember, both use the same TSMC N3E process node, which means a wafer costs the same. As far as I know, the A18 Pro was only used in the iPhone 16 Pro and Pro Max. And Apple also only used A18 Pros with all 6 GPU cores enabled, which means chips that have a production defect couldn't be used. As we saw, the GPU is the largest function block on the A18 Pro, which means if there's a defect, there's a pretty good chance it's affecting the GPU. Using a binned A18 Pro is genius because it means Apple can now finally use all the A18 Pros with a partial defect in the GPU area. I'm sure Apple has been collecting these bin chips ever since they started producing the A18 Pro back in 2024. And using an iPhone SoC that is designed for even lower power than the already efficient M-series chips, Apple can get away with using a cheaper and lower capacity battery while still getting good battery life. The A18 Pro also allows Apple to design a smaller logic board for the MacBook Neo. Not a massive difference, but when every dollar counts, it does help. And lastly, the A18 Pro already comes packaged with 8 GB of DRAM. Yes, in theory, Apple could tell TSMC to start packaging the A18 Pro with more memory. But that would not only be expensive, but also mean they couldn't use older A18 Pros that were already produced for the iPhone 16 Pro. The M3 MacBook Air still came in a base configuration of 8 GB DRAM and 256 GB SSD. That was not that long ago. In my opinion, the MacBook Neo is the smartest way Apple could have built a low-cost MacBook, and the A18 Pro is the central piece of the puzzle. I know I've been missing in action a bit in the last couple of months, but this is about to change. Many projects and videos are in the works. Here's a sneak peek of an amazing M1 die shot from Fritz & Fritz. And you can also find me over on the Semi Analysis YouTube channel. I hope you enjoyed the video. and see you in the next one.